Hello students, I hope that all of you are safe and healthy. So let us start discussion on relativistic quantum mechanics. Till now we have studied non-relativistic quantum mechanics, and we know that this Schrodinger equation is the non-relativistic wave equation that gives the dynamics of non-relativistic particles in quantum mechanics. And we use this Schrodinger equation to solve many potential problems. Even we use this equation to solve hydrogen atom problem. And also you have learned perturbation theory, scattering theory, all these things using Schrodinger equation. But for example, when we want to discuss, say, hydrogen atom, where this electron in the atom is highly relativistic particle, the Schrodinger equation is not enough to describe the system. And we have seen that this Schrodinger equation cannot give you the exact eigenvalues or the energy levels of the atomic electron. So we need a relativistic version or relativistic extension of this Schrodinger equation. So the equation that should be consistent with special theory of relativity, or we actually demand that the wave equation should be consistent with the Lorentz transformation of the special theory of relativity. And that branch is actually that wave equations and the quantum mechanics, which is actually consistent with this special theory of relativity, is called the relativistic quantum mechanics. One advantage of relativistic quantum mechanics that we'll see is that spin is the integral part of the relativistic wave equations. For example, in Schrodinger equation, there is no information about the spin. So when you discussed electron inside the atom, we did not have any information about the spin, and we had to put in as an additional information the spin actually as an additional information. But in relativistic quantum mechanics, that comes naturally within the equation. So you don't need to actually put that information by hand. So in this course, we will discuss two relativistic wave equations. One is for spin 0 and one is for spin half. So when we will discuss, then we will see that how naturally they comes. So before going into the development of the wave equations, we need to first fix this notation and conventions in the special theory of relativity that we are going to use. And we know that in special theory of relativity, time and space are considered in the same footing. So they come together. Unlike the non-relativistic formalism where x or the position you consider as some operators but time as some parameter. So we know that this 3 vector, that is the 3-dimensional spatial vector R, is actually given by this 3 component x, y, z, or we use this convention x1, x2, x3 in place of x, y, z. Now in the 4-dimensional space-time, we define a 4 vector, that is a 4 component vector x mu with x0, x1, x2 and x3. Or you can write in short that x mu is x0 and xi, where this I goes from 1 to 3, and this x0 is the time component. This is given as c into t. So this c is multiplied so that this all this x0, x1, x2 and x3 have the same dimension. And another notation that we use very frequently, that is we don't put that superscript mu. So basically when you write this x, that means this 4-dimensional vector x0 and this r vector. And we define this derivative operator or differential operator del del of x mu is equal to del of mu. Notice that when you write this subscript mu and then in the del del of x mu, this mu is actually superscript. Okay. And that you can write in these 4 components. So basically this is 1 over c del del t is the time derivative, and this is the spatial 3-dimensional derivative. Now we generalize this distance between these 2 points in space to the distance of 2 space-time points. So for that, you consider the 2 points separated by a small distance in all the coordinates x0, x1, x2 and x3. That is actually given here. Now we define this interval d square is equal to g mu nu dx mu dx nu. So here we have used the convention that sum over repeated indices. So for example, here mu is repeated here and nu is also repeated here. So both mu and nu are actually summed over. So we have not put that summation here explicitly. So whenever we will see that indices are repeated, we will assume that these are summed over. And this g mu nu here, sitting here, is the property of the space-time. So this is actually called the metric of the space. So for the Minkowski space, where this is basically the flat space we live in, then g mu nu is given by this metric. This is basically a diagonal metric, where only this time component, so g00 is +1 and all the spatial part, other things are -1, diagonal elements. And in the Minkowski space, g mu nu with mu nu lower index is same as the g mu nu with upper index. And once you actually use this metric here, then d square is actually written like this. So d square is c dt square minus this dr square. This is the spatial distance between these 2 points, this dr square. Now the general Lorentz transformation you can write like this, that x prime mu under some Lorentz transformation. So basically under the Lorentz transformation, x goes to x prime, then x prime mu is equal to lambda mu nu x nu, where this lambda mu nu is some Lorentz transformation operator, which is a 4x4 matrix because of this 4-dimensional space-time. And one can show that this d square is invariant under Lorentz transformation. Okay. So this distance is a invariant quantity. And here also you use two different definition of the vectors. One is called the contravariant vector, that is generally denoted by this mu index as the superscript. So a vector that transforms like x mu, so whatever any quantity that transforms like this spatial coordinate x mu, so that is given by this x prime mu is equal to lambda mu nu x nu under the Lorentz transformation, then we say that this is a contravariant vector. And then we define another that is called covariant vector A with lower index mu. That means anything that transforms like this del del x mu or del mu. Okay. So that is called the covariant vector. And this covariant and contravariant vectors are related by this transformation. Again, here this nu is repeated, so there is a sum over nu. Okay. And so from covariant to contravariant and contravariant to covariant, we can actually go by using this formula. So you can see that this covariant vector x mu is actually x0 minus x1 minus x2 and minus x3. So because of this g11, g22 and g33, these are -1. That comes from this 3 minus 1 sitting here in the g mu nu. Okay. And you can define the scalar product between these two 4 vectors. Say A and B are two 4 vectors, that is actually defined by this A upper mu and B lower mu, or you can write also A lower mu, B upper mu, the same thing. And that is equal to A0, B0. This is the time component of this, and these are the spatial 3 vectors dot product. As we have defined that this del mu, this differential operator with lower mu, is defined like this. So you can actually define this del mu with upper index, so basically this contravariant derivative as g mu nu del nu, and that because this negative sign in the spatial part of this g, you get a negative sign here. And then you can define this D'Alembert that we will use, which is del mu, and then you get basically this second order differential operator. And you know that the relativistic energy, that E you define as gamma mc square, or gamma is given by this thing. And the relativistic 3 momentum P is as gamma m and v is the velocity of this particle, and this m is the mass of this particle. So energy momentum for vector you can define as P mu is equal to E by C. So this energy comes as the zeroth component and the three spatial dimension, spatial momentum component. And then if you take square of that, P square is equal to P mu and P mu, then you will get E by C square minus this P vector square. And if we just put that E by this expression of gamma mc square and P vector is gamma mv, then you will show that this P square is equal to mc square, m square c square. And another quantity that we will use very frequently is that P dot x. So P and x are all 4 vectors. So this is basically P mu and x mu is equal to Et minus P vector and dot x vector. So that actually fixes our convention and the notations that we are going to use. So now let us come to the relativistic wave equation. So first equation that we are going to discuss is Klein-Gordon equation. Actually, this equation was first developed by Schrodinger himself. When he first when he first wrote down the non-relativistic wave equation, he also wrote that extension of that for relativistic cases. But later on, Klein and Gordon developed this thing and is known as Klein-Gordon equation. So the strategy is very simple. For non-relativistic energy momentum, we have this E is equal to P square by 2m. And now we use the correspondence principle. So basically we write this E as an operator, del H cross del T, and for this vector P you write as minus IH cross del operator, special derivative. So basically this E phi is equal to P square by 2m phi, you write that wave equation, and for E and P square you write their operator form, and what you get is basically free Schrodinger equation. Now extend this algorithm or this prescription for the relativistic energy momentum relation. So we know that for relativistic particle E square is equal to P square C square plus m square C to the power 4. So now I write that E square phi is equal to that P square C square plus m square C to the power 4 phi. And then we use this operator form or the derivative form using this correspondence principle, and you get this equation. And once you actually simplify a little bit, you can write in this compact form. So this box is the D'Alembertian operator, and this is the m square c square by h bar square phi is equal to 0. So this equation is known as Klein-Gordon equation. So this is very simple equation. So what are the properties? So here you can see that this phi x, where this x is actually this 4 space-time coordinates. So it actually depends on t and x vector, is a single component field, just like the Schrodinger equation. Okay. The psi or the phi that you get from the Schrodinger equation is similar to that. And this box operator, this del mu, this is a Lorentz invariant quantity. Okay. So the Lorentz invariance of the Klein-Gordon equation, because for the equation to be consistent with the special theory of relativity, we require that this wave equation should be invariant under the or covariant under the Lorentz transformation. Okay. So for the Lorentz invariance of the Klein-Gordon equation, so phi, since this operator, if we just look at this equation, so you have this del, this box operator multiplied with phi. So since this quantity is scalar, so this also has to be Lorentz scalar, so that there is no change in the equation. So it requires that phi also has to be Lorentz scalar. So this Kg equation actually describes the dynamics of a scalar particle. And since you have only one component, you cannot have any information about the spin. So basically this actually corresponds to the spin 0 particle. Now if we just look for the plane wave solution of this Kg equation, the Klein-Gordon equation, you write that phi x is equal to n into 2 to the power I p dot x, where this p and x are the four component vectors. So that in the explicit form you write like this. Now you put this solution in the Klein-Gordon equation. So this, when you put in this equation, this phi, then you get that E square is equal to P square C square plus M square C to the power 4. So E is equal to plus minus of square root of this quantity. So you have both plus and minus. So positive and negative energies both are actually allowed by the Klein-Gordon equation. But here we have a problem. Since now we have negative energy solution, right? So if we consider any particle is in some positive energy state, and then I can actually extract energy from that particle and push it into a negative energy state. And I can actually extract any arbitrary large amount of energy from the system by pushing it into more and more negative energy state, right? Because for large momentum p, this energy becomes large, so I can have arbitrarily large negative energy, and the system becomes unbounded from below. So any particle which is in the positive energy state, I can always have some perturbation and push it into a negative energy state, and it can go into a large negative energy, infinitely large negative energy states, and it becomes unstable. So we don't have actually a stable particle. We cannot have any stable particle solution. Then you may say that, okay, let us assume that these all the negative energy states are unphysical states, and we just throw away all these things. So I say that this particle cannot, only these positive energy particles are physical particles, and negative energy particles are unphysical. But the problem is that when you actually throw away these negative energy solutions, then one of the basic postulate or basic requirement of the quantum mechanics, that the eigenstate of the Hamiltonian form a complete basis state, that completeness relation is lost, because half of the basis you are actually throwing away, or half of the solution you are throwing away. So when you actually throw this half of the basis, any other state you cannot expand in the basis of this eigenstate of this Hamiltonian. But you may say that, okay, it is not so serious. But another serious problem is that even if I assume that, okay, all the negative energy states are unphysical, but if you have a particle in the positive energy state, I can have some perturbation which will actually cause this particle, or will make this particle to jump to a negative energy state. Since negative energy solutions are valid solution of the Klein-Gordon equation, we have no means to stop that process. There is some interaction, or you can write down some Hamiltonian that will actually allow this particle to jump to a negative energy state. And when it goes to negative energy state, again you are actually back to square one. You have the same problem, that you have it becomes unbounded. So this interpreting negative energy state as unphysical does not solve the problem. Okay. So another problem you can see is that if you just look at the conservation law, so you just look at the continuity equation, because continuity equation actually gives you the conservation of probability. So from the Klein-Gordon equation, you can derive a continuity equation like this. Just if you remember that in Schrodinger equation, we had the similar type of equation, where this rho is the probability density and J gives you the probability current. So that tells you that if at any point or in any area the probability of finding this particle actually decreases, then the probability is increasing in the area outside that region. So some probability is actually flowing out from this area. That is actually given by this J. And if we just do this Same exercise here from the Klein-Gordon equation. You can derive the similar equation here. But here then the rho takes this form like this. So here you have this del T of phi and phi star and this equation, and J, this probability current is this. Now to interpret this rho as the probability density, it must be a positive definite quantity. Probability cannot be negative. So if you just look at the plane wave solution for this phi and you put it that plane wave solution here, what you will see is that rho takes this simple form where this capital N is the normalization constant, so you have mod n square, and this E is the energy. So this rho is negative for negative energy, right? So you cannot interpret this quantity rho as probability density. So you have another problem. So basically we have two problems with the Klein-Gordon equation. Both are actually associated with a negative energy solution. Once we allow this negative energy solution, the system becomes unbounded from below and you don't have stability, you don't have any stable particle, and you cannot have a probability density. You don't have the valid definition of the probability density. Okay. So due to these two problems, people did not accept Klein-Gordon equation as the desired relativistic wave equation. So they thought that this equation is sick and you cannot use this equation and abandoned it. Later on, Feynman and Stuckelberg interpreted that positive energy states as particle and negative energy states as antiparticle. And this type of explanation actually require quantum field theory rather than this quantum mechanics. So though in the quantum mechanics Klein-Gordon equation was abandoned, but in quantum field theory it is still a valid wave equation which describes spin zero or scalar particles in quantum field theory. So once you actually don't accept Klein-Gordon equation as your valid quantum relativistic quantum mechanical wave equation, so people are searching for another wave equation which is actually free from all these problems. And in the next part of this course, we'll learn about the another equation which was developed by Dirac and trying to circumvent all these problems encountered by Klein-Gordon equation. Okay, so that part we'll discuss later. So stay safe, stay home, bye. And if you have any question, please let me know. Write me an email and I will answer you.